So in class we've been talking about empirical formulas, and one of the ways that we can determine the empirical formula from data is looking at combustion analysis. And when we look at combustion analysis, what we're going to do is we're going to focus on the formation of carbon dioxide and the formation of water when something with carbon and hydrogen reacts with oxygen, basically. And so we're going to see what kind of information can we get from the mass of carbon dioxide and the mass of water that tells us something about our compound. Okay, so we're going to work through an example together and talk about how we're going to utilize this information. So what we're told is a compound was known to contain only the elements of carbon, hydrogen, and nitrogen. The combustion of 5.1 gram sample of the unknown compound was found to produce a certain amount of carbon dioxide and a certain amount of water. So one thing we'll notice, it doesn't tell us anything about nitrogen. So there's nothing here containing nitrogen, so we're going to have to see how can we identify the amount of nitrogen even though we're not directly given some kind of substance, compound that contains nitrogen. So in addition to that, the molecular mass of that compound was identified to be 162 grams per mole. So from this information, we want to determine the empirical formula. Reminding us, empirical formula is the lowest whole number ratio of the moles of each element in a compound. In addition to that, we want to determine the molecular formula. So that is the actual number of moles of each element in 1 mole of that specific compound. Okay, so looking at in a mole, or how much is in a 1 molecule. So let's unpack how we're going to do this. So let's start with our empirical formula. So in class we've talked about empirical formulas, and we remember that empirical formula, we need to get to mole ratios. Well, before I can get to the mole ratios of carbon, hydrogen, in this case nitrogen, I need to first identify what is the mass of carbon, hydrogen, and nitrogen that I have. So we'll notice that we don't have any information that tells us the mass of carbon and the mass of hydrogen or the mass of nitrogen, but what we do know is that I have 13.835 grams of carbon dioxide. Well, all of the carbon in my carbon dioxide came from the carbon in my compound. So this is going to give me the ability to identify the mass of carbon in some way. Additionally, if we look at the data that we know that we have 3.969 grams of water. And again, what we notice is that all of that hydrogen that we have in our water, it came from the hydrogen in our original compound. So that gives us the ability to identify the mass of hydrogen here. Well, what we also know is that the sum of the mass of hydrogen plus the mass of carbon plus the mass of nitrogen is going to equal our 5.100 grams total that we had for our compound. So that's going to give us the ability to identify the mass of nitrogen. So now that we've kind of broken down step by step what we're going to do, let's go ahead and work through it. So we're first going to start right here. We're going to think about if I have 13.835 grams of carbon dioxide, how am I going to identify the amount or mass of carbon dioxide in there? Well, if I'm going to relate this, I'm first going to go ahead and find out how many moles of carbon dioxide I have. So I have 44.009 grams of carbon dioxide for every 1 mole. And then we think, what is the relationship between carbon dioxide and carbon? Well, if we go ahead and see in every mole of carbon dioxide, we don't have a subscript here, but this would be C1, I have a single mole of carbon. So now I've gone from the amount of carbon dioxide to the amount of carbon, but I need to now figure out the mass. We'll do another molar mass conversion, so 12.011 grams of carbon for every 1 mole of carbon. Let's go ahead and check to make sure our conversions are right. So we've gone from grams of carbon to moles of carbon to of carbon dioxide to moles of carbon, moles of carbon to grams of carbon, and that's going to give us our mass in grams of carbon, which is 3.776 grams of carbon. Okay, so now we have the mass of carbon here. Right, that's what we were trying to figure out. Let's do our next step, and that we need to figure out what mass of hydrogen we have. So again, we start with our 3.969 grams of water. Again, if we're going to relate the hydrogen to water, we're going to use our molar mass, so 18.015 grams of water, because again, this is not all hydrogen, it's water, for every 1 mole of water. And then we want to think, what is the relationship between the moles of water to the moles of hydrogen? So we notice we have a subscript here of 2. That means I have 2 moles of hydrogen for every 1 mole of our water here. And then finally, we can go ahead and find the mass, 1.008 grams of hydrogen for every 1 mole of hydrogen. Again, that's our molar mass. And again, if we track our conversions here, making sure that we're ending up with the mass that we want. In this case, we want the grams of hydrogen, which would be 0.444 grams of hydrogen. So now I have the mass of hydrogen. Final step, we're going to use the relationship that the sum of all 3 of these is going to add up to my total. Okay, so we know that we have 5.100 grams. Total is going to be 3.776 grams of carbon, 0.444 grams of hydrogen, plus, I'm going to call it X grams of nitrogen. So we're going to find that X is 0.880 grams of nitrogen. So now I know the mass of each of my components, carbon, hydrogen, and nitrogen. Now we're going to go ahead and go backwards now and go to our moles and then to our mole ratios. So this is going to look a little bit more familiar to what we've done before, where we start with maybe masses directly. We had to do a little bit of an extra step, but now the rest of the process is very similar, where we're going to go from our 3.776 grams of carbon and our 0.444 grams of hydrogen and our 0.880 grams of nitrogen, and we're going to convert each of these to moles. So we can again use our molar mass, use a molar mass of hydrogen, and finally the molar mass of nitrogen. And so we're going to find that we end up with 0.314 moles of carbon, 0.440 moles of hydrogen, and 0.0628 moles of nitrogen. So now we're almost there. We almost have our empirical formula, but we remind ourselves that when we're looking at this, each of these need to be whole numbers. And the way we get to like the first step is we're going to divide by whatever our smallest number is. So in this case, we're going to divide by the 0.0628, because that's going to make the moles of nitrogen 1. So we divide by our 0.0628 for each of these. And again, if we do something to 1, as long as we do it to the rest of them, we multiply or divide by the same value. That keeps our ratio between the carbon, hydrogen, and nitrogen moles the same. This gets us 5, 7.006, which we can round to 7, and then we get 1. So just by dividing by our lowest one, we get to whole numbers for all 3 of our carbon, hydrogen, and nitrogen moles. And so then we take all of these and we combine them together down here, and we would get C5H7N. So that would be our empirical formula, which could be our molecular formula, or it could not. And remind ourselves the only way we get from there to our molecular formula is if we have our molecular mass. And in this case, we had that data, we have the molecular mass data, and we go back and we see the molecular mass that we're given is 162 grams per mole. So what we need to figure out now is if my empirical formula as it relates to my molecular formula. Is my molecular formula C5 times 2 or 3 or 4? And so we're going to just put n here to say that that's our multiple. That's how much large multiple times it's larger. If it's 1, it's the same. It's 2, it's twice as large, 3, etc. The way we identify n, or how many times larger our molecular formula, is with the number of carbon, hydrogen, and nitrogen atoms. Same ratio, though, is by looking at our molecular mass and dividing that by our empirical formula mass. So our molecular mass was given to us, 162 grams per mole. So that was given or provided in our problem here. Then our empirical formula mass, we're just going to take what our empirical formula is, add up 5 carbons times its mass, 7 hydrogens times its mass, 1 nitrogen times its mass, and we're going to end up getting 81.118 grams per mole. And we calculate that from our empirical formula, C5H7N. So go ahead and throw it in our calculator. We get 1.997, which is pretty close to 2. So now we can go ahead and say, well, my molecular formula is actually twice as big as my empirical formula. So it's going to be C10H14N2. And again, that's C5 times 2, H7 times 2, and 1 times 2. So now we have the ability to identify what our molecular formula is. Again, the same ratio of carbon to hydrogen and nitrogen, 5 to 7 to 1, but it's scaled up a little bit larger because this molecule actually contains twice as many carbon, twice as many hydrogen, twice as many nitrogen atoms. Okay. So now I want to go ahead and recap real quick and thinking about our combustion analysis when we're looking at this. When we look at combustion analysis more generically, what we're going to see is we're going to be given some kind of mass of carbon dioxide, which is going to get us the ability to get to the mass of carbon, because all of that carbon and the carbon dioxide came from our original compound, which then gets us to get ability to get to the moles of carbon. Then we go and we see the other data we might have is the mass of water, which gets us the ability to get to the mass of hydrogen in our original compound when we combusted it. And again, all that hydrogen came from our original compound. And then that gets us the ability to find the moles of hydrogen. And then if we have any other element in addition to carbon and hydrogen, and a lot of times we see this as maybe oxygen or nitrogen or sulfur, or maybe something like fluorine or chlorine, some other nonmetal that's with it, we can then go ahead and find the mass of that other element. And the way we do that is we take the total and subtract the mass of hydrogen and carbon that we have, because the rest of it's got to be that other element. We're only going to see one of those. We're not going to see something that contains carbon, hydrogen, oxygen, and nitrogen. Right? We're only going to be able to do this elemental analysis by looking at one additional element, which then gets us the ability to find the moles of that other element. And then we go ahead and we take all those pieces together, and that's going to get us the ability to find our empirical formula. So again, we're going to continue to practice this in class. Hopefully this helps us prepare and think about how we use combustion analysis, just the extra step here that we got to do to find the mass of our elements of carbon and hydrogen simply from the mass of a compound that contains those two elements.